What we're doing is trying to kind of find this sweet spot in the trade-off between bias and variance, which is another way of conceiving of this problem of we want to use a model which is rich enough to capture all of the true information, the true signal in the data, but not so rich that it overfits the data. And if we use a model which is too simple, and so the parameters say are close to 0, right? This might set a lot of things to be 0 or close to 0. It won't generalize well to data that we didn't use. In fact, it'll already have poor prediction error on the data set we come in with. If we use a model that has a lot of parameters, we can expect that the parameters can fit our data exactly, but as a consequence, when we look at new data points, so we try to make inferences about it, the inferences will be very poor, or equivalently, it will generalize poorly to new data. And the idea of this was to sort of add this extra idea. So we had likelihood, log likelihood, as our main tool of inference. Right? We said that the principle of log likelihood says that you have this, or maximum likelihood principle says we have a function which we can think of as a likelihood or the log likelihood. It's a function of both the parameters and the data, and we should choose the data that makes the parameters most likely. Right? And so this function, as I increase the number of parameters, I increase the complexity of my model, of course this function will always go up, the data will get more likely. And so it's kind of blind to this variance side of the phenomena. It understands how to reduce bias, but not how to deal with variance or overfitting. And so what we propose is that we should add to this another term, which is a function of the sample size. And it's not immediately clear why it should be a function of the sample size, but I'll explain a little bit more about that in a moment. And a function of the parameters, or the number of parameters. So let's change this to, last time I had p there, but we can say g of theta. So some function of the parameters which should measure somehow how big they are. So last time we talked about this function being just the number of parameters, or the number of parameters divided by 2, and this function being just 1, or log n. And there's a lot of work that's done in thinking about other alternative ways of measuring the complexity of the model. So you can measure how far away is this vector of parameters from 0. Right? And you have a choice of distances to use. You can use L2 distance, L1 distance, or L0 distance. L0 distance is just count the number of parameters which are non-zero and call that your penalty. But there's other choices you can make too, and those other choices have some advantages. So the two criteria that we mentioned is this Aic criteria, which is just you take the log likelihood function and you subtract the number of parameters. And another way of writing the number of parameters is to say it's the L0 norm. Then there's this Bic criterion that we'll mention in a second, which uses a little bit more of this flexibility. It's the number of parameters divided by 2 times log n. So the point is that while this one will always naively tell you to go to a bigger and bigger model, a more complex model, these two will give you a reason to stop. Right? You'll increase your complexity of the model, and at some point this term will overwhelm this term, and it'll start to go down. So both of these give you an objective function that looks like that, and we'll let you choose a best model. Of course, in the kind of models we've talked about, this is not a one-dimensional space. Instead, we have like a lattice of models. Right? We have like a very simple model like independence, and we get more and more complex models. And they can depend on each other. And so each of these points will get a score. And the idea is that for small sets like this, we can just evaluate these two things at every point and pick the smallest number. And for big sets, when there's a lot of parameters and this lattice grows quickly, we have to have some heuristic procedure for searching it, because it would take too long to search over every possible node, every possible model. Okay. So stopping short of a full derivation, what I want to do is tell you a little bit about why these functions make sense. So this one, right, subtracting the parameters is already something we're doing a little bit when we think about something like the delta g squared, right? Because we think about this thing, and we're comparing it to this degrees of freedom, which is equal to the number of parameters, right? So we're already kind of doing that when we're doing the g squared and asking is it significant. But there's a more precise way to justify it, which I'd like to talk about now. So you can think about there being two likelihood functions.
Yeah. So I was wondering, so here, the target function here we are talking about is logly likelihood. So when we want to penalize our target function, usually we just add up the penalty function, right? But here it seems to me it's just we kind of abstract our penalty function. So is that always true that when we want to penalize our target function, we just add a term rather than just to subtract the term? Subtract the penalty.
Right, so here we're considering a penalty which is subtracted. If I was looking at the e to this, then it would be a multiplicative penalty.
Yes, the target function, which is log, L x theta minus the f of n times g of theta. So I was wondering why here we use the minus the g of n and times the.
Oh well, that's sort of what I'm going to talk about how you could find such a formula.
For example, for the Lasso case, and also even
We'll get to less. Let's not. Yeah, we'll talk about that towards the end. Okay. Okay. So we have two likelihood functions. You could think about there being a true likelihood function and a fitted likelihood function. So this is the true likelihood function that's generating the data, that corresponds to the function generating the data, and this one is our estimate of what the likelihood function is. And we want to compare them. And a natural way of comparing two probabilities, so these are just probability distributions, if you think about them as a function of the data, right? These are probability distributions for the data, x. And to compare two probability distributions, to take the distance between them, one of the most common ways to do that is this thing called the KL, which stands for callback Leibler distance or divergence. So that's kind of what you should think of from a likelihood framework. That is the natural model of the difference between distributions. For example, we can think of maximum likelihood estimation as minimizing this divergence between an empirical distribution and a point on the model. So we want to think about the KL divergence from between these two functions, between the true likelihood and the fitted likelihood. So suppose we have a set. So in this case, we have a finite set of models. So we have a set of models, M1, M2, MM. For example, this might be the independence model. Maybe this is a joint C, or you could think about this as being, intercept only, intercept plus B1, whatever, something like that, right? We have a set of models, and we have a fitted probability distribution function, or likelihood function, for model J. Right? So I pick a model of this, then I fit the parameters, and I get out a probability distribution function of the data, or equivalently a likelihood function. And so our model says that the outcome of the probability of outcome x, which you could think of as being a single data point or as being the whole data set generated by the likelihood function, is fj theta star x. Just another way of writing a likelihood function. And it has a log likelihood, which is usually more convenient to work with, which looks like, well, I sum over all observations, log fj beta star x. So our loss function, sort of how far we've gone wrong, is the Kullback-Leibler divergence between the true distribution and the estimated distribution, the one that we've figured out from our model. And we can think about our goal now as, so the sort of the first order goal, right, is I have like an empirical distribution, I try to fit it to the estimated one, and I can always get a better fit by making my model bigger. But now I want to think about before I've rolled any dice, before I've thrown any darts, right, before my experiment, there's this true distribution, and there's this estimated distribution, which is a random variable, right, which will change depending on what the outcome is. And so what I'd like to do is minimize the expected difference. Right? I think about this whole thing as a random variable now, because this is a random variable which depends on the data, right, which in turn depends on this distribution. So this whole thing is random. This loss is random, and I want to minimize the expected loss. So that, with respect to the true distribution, minimize df f star. So this is a new idea in the sense that this can take into account both bias and variance, right? Like if I'm minimizing this function, if I overfit, I get penalized for it. If I have a procedure which overfits, the difference between these, the true and the empirical will be big, because it'll be exactly fit to the data instead of to the best estimate data. So this is a strategy for baking in that penalty that's fairly reasonable. And if I calculate what that is, well, by definition of KL divergence, the divergence between f and f star is just the sum over the observations f of x log f of x over f star of x. Let's say this is dfg, just so I don't get too confused here, okay? And if I look at dff star and calculate it, I get some number, constant, which is the sum f of x log f of x, minus some other number, which is a function of both f and f star. In other words, this quantity breaks up into two pieces, right? Because the log of something over something is the log of this minus the log of that, right? So it's a constant, and we know what this constant is called. This type of thing is an entropy, right? Probability, sum over the outcome is probability of the outcome times log of the outcome. So this is h of f. And then I have left over this other piece, which is like the adjustment, okay? So fixing the true distribution f, I don't care about the entropy of f because that's fixed, right? That doesn't change when I change my model. Only this part can change. Only a can change. And so here, a of f star is the sum over the observations f of x log f star of x. So that's sort of the quantity where something interesting happens that includes the estimated distribution. Okay, so if we want to minimize this number, we want to minimize the expected risk, we should try to right, we have the entropy minus this thing. We want to maximize this thing. Right? Maximize the part that gets subtracted, and that will minimize the part that will minimize the total. So minimizing risk or minimizing expected error, linearity of expectations. Right? If I take the expectation of that difference, it's the expectation of the first thing minus the expectation of the second thing. The expectation of the first thing is fixed. Right? Expectation of C is fixed given the data minus expectation of this other guy, A. That's where we have something we can do. So minimizing this total error, the total amount by which we expect that our fitted model will differ from our true model, is the same as maximizing this. Okay? Now, if I wanted to plug into my computer a maximization problem and try to solve that, there's a problem, right? I can't do that. Why can't I do that? This is just a function, right? It's a of f star. And I observe some data, and I want to solve this problem. I can't do it because I don't know what the true distribution was. I don't know what f was. All I have is the data, and I have my model. So what do we usually do when we don't know a distribution? We use a plug-in estimate, right? We just do the best we can with the information we have. So we estimate it using this f star instead. So we estimate f, assume that f and f star are essentially the same. Of course, this has problems because we're using the model to sort of deal with itself. So this is a biased estimate. It's not unbiased because it doesn't know which model is correct. But fortunately, with some work that I won't repeat, but you can read about, the bias can be shown to be approximately this quantity, sometimes denoted the size of the model. Remember, we're in model J, which is equal to the number of parameters. And you think the justification has to be something like the way we get the chi-squared distribution asymptotically, and it has the right degrees of freedom, right? It's a similar argument. So the idea is that the AIC is just the likelihood corrected for this bias. And L minus P is an approximate unbiased estimator of this quantity, expectation of A, or at least maximizing this quantity will maximize this quantity. Okay, I might have lost a constant or something, but solving these two maximization problems are equivalent, at least approximately, under certain conditions. Smoothness, regularity of the model. And so that's kind of where this L minus P comes from. It comes from an argument that we ought to minimize this difference, the expectation of this difference. We make some approximations, and it turns out to be about that. Which, if you're thinking about G squared and degrees of freedom, is not surprising.
Yeah, excuse me. I was wondering whether it's true that the G star equal to F star. Like, this is what you are saying here, right?
Yeah, I was saying this is the definition of D as a function, and I'm plugging in F star.
And so, were you saying like plug in the estimate using F star? Is that only for the term, the expectation of A at F star? Because otherwise, if you plug it in over there, you're just going to the divergence is 0, and they'll be the same thing.
Yeah.
So now are you essentially just turning the A term just into the entropy of F star?
No, it's not quite that.
That's how you defined it, or said that it was over there. It was like F log of F, so we're doing F star log of F star.
Yeah. I'm going to make a note. I'll write up a little, the full derivation of it. It's not very hard, but I don't remember it up there. But the idea is just to use a plug-in estimate, basically. In other words, we're doing the estimate expectation of A F star, and this is with respect to F, is approximately sum over X, F star of X. Yes, I guess it is the entropy, right? F star of X. Yeah, so I guess it is approximately the entropy, but then we know that you have to compute the bias, and the bias is an additional step. Yeah. Okay, so what we're doing is we're minimizing the kind of the wrongness of the error, and this, another way of saying it is that this AIC tries to choose a model with the highest expectation with respect to the truth, likelihood with respect to the fitted of x. Right, so just this little, the inside part is what we do with just straight maximum likelihood estimation. Find the maximum likelihood estimate is maximize the likelihood with respect to fitted. And what we're doing with the AIC is essentially adding a new expectation on the outside. What do we expect given the true? Find that procedure. And the other observation to note that if you remember, if you took our 501, or you know a little about linear regression, then this criteria AIC is equivalent to what's called Mallow's CP. So in other words, if you apply the logic of the AIC, you can get to the Mallow's CP. If you don't know what that is, then don't worry about it. But if you remember it from regression, then great. Okay, so what's next? The other one, Bayesian information criterion. Let's see how we can get to that. Minus 2L plus P log N. Now, we don't do a lot of Bayesian estimation in this class, but I think it is it's a very important method for inference, and it's especially important in situations where the frequentist methods that we use don't work very well. They hit boundary conditions, they hit other issues, or you don't have enough data in the sense that you have way too many variables. Your number of variables is bigger than your number of data points, or something like that. So what's the basic idea of the Bayesian approach? And to model selection. And it's also good when you just have a lot of knowledge about your data set that you need to incorporate. So for example, if you're trying to estimate gene or protein, some sort of interaction networks, which is a common pastime, or doing omics of some kind, it often makes a lot more sense to use a Bayesian technique because we have so much information about, you have this whole body of scientific literature that says which interactions exist already, and you want to incorporate that prior knowledge somehow into your new test, right? If you just do it blind without using any of that information, it's very unlikely that you're going to get the right answer. Okay, so the idea is that we have some models again. So we have some number of models, and again, you should think about these as being, in our context, something like, I have independence model up to some other complex model, or different choices of which main effects and which interactions to include in a logistic regression. And now we have an additional piece of information, two additional pieces of information, which is we have a prior on the models. That means we have a judgment before we see any data, or based on previous data that we've seen in different experiments, we have an idea of a probability distribution over which models are most likely. So maybe we think independence is very unlikely, the saturated is very unlikely, for example, and maybe we think it's quite likely that it's one of the conditional independence models for some reason. Right? So we have some prior distribution of models, we have a prior judgment of what probability we think each model should have. And then second, we have another prior on the parameters of each model. That is, we have a probability distribution on the parameter vector for a model, given that model. Okay, so I have a probability of which model I should use, and then inside of that, I have a further probability distribution on which parameters I use. We haven't seen much of this. We mentioned a little bit when we talked about the beta binomial and things like that in the very beginning. Right? So you could think about, for example, in a binomial or Bernoulli distribution, if I start out with, I'm flipping coins, and I think most likely it's close to 1/2 the bias, right? So I have coin, right, or probability p for the coin, and maybe I think that almost all the time that the true probability is going to be close to 1/2, and it's very unlikely that it's 1 or 0, right? that would be a prior on the parameter. Prior on the model would be whether I thought it was more likely that the coins were fair or biased, for example, or whether the coins were somehow related to each other. Okay, so then combining those two pieces of information, we obtain posterior probability of a given model. Which is probability of the model, a particular model, one of my lists of models, given the data. Right, that's really what we're interested in for model selection, is finding the most likely model given the data. But now this is, instead of the simple likelihood function situation, this is a more complicated calculation. So just by phase rules, probability of that model, which was from our prior, probability of the data given the model, which involves performing a fit, and then the probability divided by the probability of x, which is the true probability. This has a fit procedure in it. And that quantity is proportional to probability of the model times the probability of x given mj, because I can get rid of this thing. That's not part of my procedure. Thinking of the data as fixed, which is in turn proportional to probability of this model, my prior probability of the model times an integral, probability of the data given the parameter vector and the model, probability of the parameter vector given the model d theta j. So this is my parameter prior. And it's a very reasonable thing to do kind of full Bayesian inference where you always make these sorts of calculations. It often becomes computationally very difficult. You need to run Markov chain Monte Carlo and other numerical integration, other fairly exotic sometimes techniques in order to solve it. And you could think about BIC as being, well, I don't really want to do all of that nonsense, but I'd like to have a little bit of the Bayesian juice in my inference procedure. It's kind of a shortcut to do some of that. So if we did this and we could compute the probability of a model given the data with an assumptions of priors, and data, then we can compare two models very easily once we have made all of those assumptions. So suppose I'm contrasting model MJ versus model ML. We have this posterior odds, it's called, which is the probability of model J given the data, calculated as written over there, divided by probability of model L given the data, which is, by this proportionality, equal to the probability of model J divided by the probability of model L. So this is the part of this which depends only on my beliefs before I began the experiment, times the effect of the data, so this is the data, and this is the model. So this is the part that I can compute ahead of time, and this is the amount that I sort of adjust these odds after seeing the data. A lot of the trick of Bayesian stuff that works well is making these kind of updates happen in a clean way. It's the idea of the conjugate prior. And you can think about these things are very similar to likelihoods. Okay, so then if the posterior odds favors this, if it's greater than 1, favors this guy, that means we choose model J. If it's less than 1, we choose L. And we have a very natural measure of sort of, either by looking at this vector of probabilities or by looking at these ratios, we can quantify our uncertainty about which model is best.
So what do you mean by like the probability of ML, like the probability of a model?
Yep, that's our prior. So we have to start with a distribution on models. So for example, say I'm thinking about the hierarchical stuff, and I have ABC, ABC, ABC. Just for simplicity, maybe I put 1/3 probability this, 1/3 this, 1/3 this, and 0 on everything else. That would be an example of the prior.
Okay, so that's just what you're saying.
So I imagine that the world first draws a model, then draws parameters, then generates data. That's the point of view. It's not usually literally true, that's what happens, but it's a way to sort of increase, have a nice kind of hierarchy of probabilities, and it often works very well in practice because usually we do have some intuition or some information about the likely state of the world for some, at least for certain kinds of models. It's very popular in finance, for example, where there are sort of reasonable things and unreasonable things, and it's too easy to overfit because there's tons of data.
Here, what the discrete summation stuff for integral, because here we're talking about the discrete data, right?
Well, summation is just a special case of integration
Right, but so
with a certain kind of measure. Yeah.
I mean, for simple when the data is very large, the discrete data.
Yeah, when everything is discrete, integration becomes summation. But here we're integrating over theta, so you would need, right? We're integrating over theta, so you would need discrete parameters.
Okay. So because it's just a simple topic,
No, because theta, remember, theta is usually like a vector of real numbers. So we're integrating over the Rn, or Rp. Right. If theta j was in Rp, was a p-dimensional real vector, this integral would be over Rp. Which is why it's more natural to use an integral. Although, in a computer, there are only finitely many floating points, so you could sort of think of it as it's a sum over a very large number. Okay, so given these assumptions, fairly strong and sometimes hard to make assumptions, we can choose which model is best by comparing these values, by comparing this posterior odds. We have a portion that comes from our beliefs before we began the experiment, and we have a portion that comes from the data. And the portion that comes from the data is called the Bayes factor. And it reflects the contribution of the data to the posterior odds. And it's by zooming in on that Bayes factor that we can get to the Bayesian information criterion. So if you think about a very simple model like this, right, where I list out all possible models, I give them all equal weight, this factor goes away because it's always 1/10 over 1/10, 1/20th over 1/20th, right? Or if the models are very close together in probability, I don't know much about which model is more likely, this factor becomes less important than this factor is the important part of the decision. So assume that the prior over models, this discrete thing, be uniform. So I place equal weight on every model. I don't think that I know anything. So PM, this thing is a constant. 1 over the number of models. It's all about choosing the largest one of these, which is very much like the maximum likelihood. But this thing is an integral, so we have probability of x given mj is the integral of probability of x given theta j. So there's the actual likelihood. Then I have this other term which incorporates the model, the prior on the parameters. This thing is basically a likelihood. And I'm integrating over theta. And you have to do some approximations, a Laplace approximation and some other approximations to this. So, okay, magic. So we do some work, and we get that the log, if you think this is interesting, I encourage you to look at the details. We don't have time to get into them, but I would bore you with them. We want an estimate of the log of this, right? That's going to be sort of my score. Right? If I have a whole bunch of these, I want to choose the max of this. I want to choose the max of the log of it. And so I've created a score for models, and I want to choose the model with the best score. So this is a perfectly good version of my best score. Yeah.
So we have to probability given the theta j and given the theta j calculate that? Do we need to add the mj given formula? Like when we calculate the likelihood.
So this, yeah, the mj is implicitly in this. This depends on mj.
Okay, sure.
Yeah, the form of the function. That's right. Okay, so what is this thing? By approximation, this ends up being log p of x given theta star, the maximum likelihood estimate, the maximizer of this, minus the number of parameters divided by 2 log n plus some error. Okay, so I've skipped all the steps, but okay, so what it spits out is that whole chain of argument that I gave you. You get this score function, which is the right score function to use. It may be hard to compute it, but there's an approximation that works pretty well, and that approximation is exactly the BIC. The BIC is what you get out after that. This is the BIC.
Excuse me, I was wondering, the number of parameters we also definitely consider including the constant term, right?
Yeah. Well, it's number of parameters in model J. So for example, in a regression, the constant term would be one of those parameters, the thing that multiplies the 1. Okay, so the idea then is that choosing the model with the best BIC is approximately the model, given that these approximations are valid, with the largest posterior probability. Given all of these assumptions. So we start with a prior distribution over models. We add a prior distribution for each model over parameters. We observe data. We integrate using Bayes' rule. We get out which model is most likely. And the BIC, so let me write that down. 1, we start with prior over models. Prior over parameters. For each model. 2, we observe data. And we possibly update that information. We integrate using Bayes' rule. Integrate that information. And finally, we get out which model is most likely, given all those assumptions. And this is an honest probability, unlike a likelihood. It really is the probability of a particular model being the true model. And the BIC, so this is the full Bayesian procedure, which is great to do, but of course requires more work and more thinking. The BIC is an attempt to sort of pick a shortcut that gives you a similar answer by making certain approximations, and certain simplifications, like the prior of the model is close to uniform, and so on. Okay.
Yeah, I was wondering one of the summary here. So when we are using the BIC, we are thinking about the people is risk neutral because we're thinking about the average of the cases, right? So how about the BIC? Do you think when people
I don't know how it relates to risk neutrality or risk sensitivity.
Because
It's an interesting question.
Thinking about the average cases, right? So kind of like instead of thinking about the worst cases.
That could be. Econometrics text or something might be a good place to look for, or game theory or something. How to think about risk aversion. Okay, that posterior, a couple of other observations. The probability of the model, given the data, if our assumptions are correct, is approximately e to the minus 1/2 times the BIC for that model, divided by the sum over all the models, e to the minus 1/2 BIC of the model. So in other words, the approximation doesn't just help you pick the best model, it actually also gives you an estimate of what, given the assumptions that you make, what the probability of each model is. This is different from a likelihood, which is not an honest probability, right? This is an honest probability. It really is a probability, with assumptions. So we get not just which model is best, but a point of view on how to measure the relative merits, to see whether two models are close, for example. So a couple of sort of practical points. The BIC is more asymptotically correct. So its assumptions and approximations are less heroic. But it often chooses too small models. So they're both great to use, and should both be helpful, especially since they're so easy to calculate, given the likelihoods. So as I mentioned, if you think about the search problem, when you have a very small space of models, finite space of models that's like, there's 10 models or there's 20 models, it's perfectly reasonable to just compute the AIC, BIC, G squared for every model in your class and pick the thing that you think is best. Great if they all agree, for example. When you have many variables, that becomes impractical. It's in fact model selection. This model selection problem with any reasonable definition, like using AIC or BIC, is an NP-hard problem. And so you need some way around it, some heuristic. You've already seen some of these, so you can do forward, for example, in a regression context, a logistic regression context, or polytomous logistic regression. You can do forward stepwise regression. And that's the idea that you start with no covariates, or you start with just the intercept and add covariates. Add more coefficients. So you increase you have sort of a fan out, right? Or maybe you pick one path that you think is most reasonable for your data, and then you just stop when the AIC, BIC goes down, whichever you've chosen, or doesn't improve, which is basically the same kind of procedure as saying, I'm going to stop when the increase is no longer significant from the perspective of G squared, the perspective of deviance. The other thing you could do is backward. So you start with everything. Start with all your interactions, your saturated model, and then drop one at a time. How do you choose them? Usually it's with the least cost. So in other words, you look at dropping each coefficient, you drop the one that costs you the least in terms of your score, or maybe even improves your score if you're using an AIC or BIC, right? Least cost makes more sense for a pure likelihood. So least cost going into benefit. So these aren't a solution to the model selection problem, right? Because there's no guarantee that either of these procedures will choose the correct model or choose the best model. But they'll usually choose a pretty good model. Okay, so there were other information criteria or scores for the model. In fact, there's quite a large industry of producing those scores and trying to justify them. Some of that exists because you can look at, there's some magic that I put in there. There's some asymptotic assumptions. When those don't hold, of course, it's not correct to use the AIC or BIC, and so there are other criteria like this widely applicable information criteria that can apply in more situations where the assumptions break down. And then there are also what you could call sort of more ad hoc, although they're increasingly well justified choices of adjustment to your function, choices of penalty. So we considered, fn equals 1, or I think 2. We considered it to be log n, and we considered g of p, this is g of theta. Let's say g of theta to be number of parameters mainly. What are other choices? So one choice is to take some function or some scalar times the L1 norm. So I don't want to get into details, but basically so if you have a vector theta, think about your vector theta as being in some real vector. There's different ways to measure the distance of the vector. These correspond to this sort of norm notation. The usual distance is called the L2 norm. It's written like that. That's Euclidean distance. L1 norm is the taxicab distance. So in this example, it would be this plus that. Right, so if I had a three-dimensional thing, it would be like this way, that way to get to the vector. It's the L1 norm, and then the L0 would just be the number of parameters, number of non-zero parameters. The infinity one will be the maximum value. Okay, so people discovered that searching over the number of non-zero parameters gives us this NP hard model selection problem. And it can be quite difficult to figure out. If you switch to this slightly strange norm where I'm measuring the sum of the absolute values of the parameters, it turns out that is often computationally easier to solve. So in other words, the problem max the likelihood minus some constant times the absolute sum of the absolute values of the parameters. This thing can be solved with convex optimization reasonably efficiently. And this leads to things like lasso, Lars, and other called L1 or sparsity promoting techniques. If you compare it to this, there's sort of there's a connection between the idea of a prior on the parameter is connected to the norm, or this idea of a norm or loss function, sometimes more or less formally. But it turns out that in that connection, this one is roughly equivalent to saying my parameter has a Gaussian distribution. One of the features or problems with the Gaussian distribution is that or with this norm as a penalty, is you think about what the derivative of this thing is, when you get close to 0, the derivative starts to get flat. And what that means is that if I use this norm as a penalty, so if I use a penalty like L minus squared norm, which in regression is called like a ridge regression, as my penalty term, when I get close to 0, the effect of making it even closer to 0 will be very small, because it sort of looks like that. That means that this one will give you will give you a dense parameter vector. So most of them will be non-zero, or all of them will be non-zero, but they'll be sort of forced to be small in the parameters. If I use this one, this roughly corresponds to a prior that looks more like it's got a big peak at 0, called a Laplace prior. For this one, the derivative as I get close to 0 in the penalty function is not 0. It's just theta. And so this one tends to choose solutions, although it's not explicitly optimizing the number of parameters, it tends to choose solutions with lots of zeros, because it can take the vector all the way to 0 without the derivative also going to 0. So for that reason, in practice, for large problems, this is much more common than the one that counts the number of parameters, simply because it's computationally a lot easier to solve. And one other thing I'd say is that a typical way to use that sometimes is to say, estimate with one of these penalized things and then redo it, having thrown out the other variables. to get the actual parameter vector.